We are again going to calculate for all these 3 points: inside, surface, and outside. Even in this case, you are going to be very amazed ki the 3 cases that we are talking, inside, on the surface, and outside, 2 cases will have the same exact variation of electric field, will have the same value of electric field as we have derived for the past 3 cases. Can you guess which case will have different variation of electric field? Think about it while I draw my very bad drawing. Okay, so it's the case of non-conducting solid. Okay, non-conducting solid. Solid means what? Shit. Sorry. Solid means what? Solid means the value of material. The materials will have the material will be situated in the volume, not only on the surface, but volume will carry some material. Like there is a ball, okay, like anything you've seen obviously what is a solid and what is a hollow thing. So a ball, okay, like the ball which we play cricket with, it's hollow inside, okay, but why, okay, you can say ki, um, that that balls we see, ball bearings we see, okay, those things are what? Those things are solid. So we are saying that ki this non-conducting sphere which we have, it's solid in nature. That means there will be charges in its volume. Charges where? It will be in its volume. Or you can just simply draw it like this also, ki the whole sphere will have material inside it. That means obviously if we are saying that this material is carrying some charge, that means charge will be carried inside the whole volume. And since the conducting nature, yeah, non-conducting nature it has, that means whatever charge a particular material have, it will have it at the same place. It will not be moving, because non-conducting spheres will not allow free movement of charges. So if we are saying, the charges are situated into whole of the sphere, that means if I take a small sphere, it's the center here. If we are going to take a small sphere, we are going to take a small sphere also. Inside the whole sphere, it's also going to contain some charges. And the value of total charge inside this small sphere, say if I am saying that this is having a radius r and the whole sphere is having a radius of capital R, will not going to be same. What is going to be same is that the value of charge density is going to be same. What I mean by that, what I am saying is ki if the whole sphere is having a charge q, and this small sphere, because we are having small sphere of small radius r, will have a small charge q, what we are going to see ki since the whole sphere is symmetric or have uniformly distributed charge, the value of charge density is not going to change. That means the value of charge divided by volume in both the cases is going to be same. Okay, even if it was a very small sphere, that means I'm saying very small, infinitesimally small, having a small radius ekdam dr or something like that, very small radius r, it also has some sort of charge which we can say to be infinitely small dq, and having a small volume you can say dv. That means if I have the charge density same, which means the value of total charge for the whole sphere divided by the volume of the whole sphere, or this sphere which is I am considering of having radius r, will have the value of charge small q divided by volume small b. Okay, or if I am saying even it's a infinitesimally small sphere, the value of charge that it will carry and the value of volume that it will carry, the ratio is going to be same for all the three. Okay, so from this you can just calculate ki what will be the value. So value will simply be equal to what? If I am just saying ki what will be the value of q in terms of rho, you can just say ki the the small charge sphere that we have, let's take this out, the small charge sphere that we have, this value will be equal to total charge, sorry, um, this value will be equal to charge density multiplied by small volume V. Okay. So let's calculate using this basic mathematics. Okay, what should be the value of electric field inside the sphere? That is the sphere which is having small r radius. So what we are going to do, understand, we have understood this. We have to calculate electric field inside, right? Let's say we are trying to calculate electric field inside, and at inside any point which is smaller than radius r. That means if this was the radius capital R, if this was the radius capital R, we are saying we are trying to calculate electric field at this point P, which is having a small radius of R. What we are going to do? We are just going to simply draw our Gaussian surface. Okay, let me just draw it with a different color so that you don't confuse it. So we are going to draw a Gaussian surface taking this point distance as our radius. And again, we are going to apply our basic principle of Gauss law. And what Gauss law says is the total flux will be equal to what? It will simply be equal to net charge enclosed divided by epsilon naught. And we have done the basic mathematics. The charge that will be enclosed inside it will simply be equal to what? Small charge q will be equal to charge density multiplied by the small volume of this sphere. So if we are trying to calculate the value of electric flux, which is E dot nothing small ds, and integration of this equals to charge enclosed, which will be q divided by uh, q divided by epsilon naught. Okay, and if we are trying to calculate the values, okay, let me just do it here. If we are trying to calculate the value, you can see the electric field again is going to be symmetric, and it will be symmetrically coming out of the integration. That means E dot ds will be equal to charge q divided by epsilon naught. The value of ds will depend upon this Gaussian surface, and that Gaussian surface will have a value of ds to be E dot 4 pi, since the radius is small r, 4 pi r square equals to the value of total charge q, and we can even substitute the value of total charge q with the charge density. So the value will be charge density rho multiplied by the value of volume, small volume v, divided by epsilon naught. So the value of electric field at inside point will be coming out to be what? Charge density, small charge density, charge density rho, volume v. What is the value of volume v? Since the Gaussian sphere is having a radius of r, we can say simply the value of Gaussian sphere's volume will be equal to what? 4 by 3 pi small r ka cube divided by what is the value of surface area? We have just calculated to be 4 pi r square. Can you see what things are getting cancelled? This 4 is cancelled, this pi is cancelled, this r square is cancelling the r cube. That means only thing remaining will be r. So the value of electric field at inside point will simply be coming out to what? Rho r by 3 epsilon naught, because the 3, which is 4 by 3, 1 by 3, it will be coming towards the denominator. So this will be the value of electric field, which will be rho r by 3 epsilon naught, which will be for a non-conducting solid sphere. Okay, this is the only thing which will be different. Other than that, if we are going to calculate the electric field, say at the point which is on the surface, which is having a radius, a radial distance of r equals to r, what we are going to see that the value of electric field on surface will come out to be equal to what? Again, we are going to apply the same principles, that we are going to have a Gaussian surface which is having the radius of r, which will be equal to what? R equals to r. And again, if we have having the value of r equals to r, again we are going to calculate the value of flux. And since this Gaussian surface will encompass all the material inside the sphere that was having the charge of q, that means the value of q enclosed will simply come out to be what? Q divided by epsilon naught. And again, the value of flux, you can say if E is symmetrical, the value of ds will only be integrated. Value will be equal to q by epsilon naught. That means this integration of ds will give us the value of the surface area of the Gaussian sphere, which is having the radius to be equal to r. That means simply the value of electric field at r equals to r will simply come out to be what? Q divided by 4 pi epsilon naught r square. Okay, and similarly, if we have a point P which is having the distance of r which is greater than r, again on the outside point r greater than r, we are again going to apply the same basic principle, which is we are going to see if we are having the Gaussian surface, if we are having the Gaussian surface, we are having the Gaussian surface having radius of r, it will also have the whole sphere which is carrying the charge inside its surface. That means the total charge inside the Gaussian surface having radius r greater than capital R will have the total charge of q, and again the value of q will be divided by epsilon naught will be equal to E dot the value of integration of ds, and this time the integration of ds will give us the value of total surface area of the Gaussian surface which is having a radius greater than r, capital R. So it will again simply come out to be equal to what? E q by 4 pi epsilon naught multiplied by small r square. So this is the value of electric field which is outside. This is the value of electric field which is on the surface, and this is the value of electric field on the inside. If we are trying to calculate, if we are trying to put it into a graph, we can just simply see what will be the value, how will the electric field variation take place. Okay, we are just going to see what will be the variation by plotting the graph. So if this was my sphere, non-conducting sphere, and this was my radius r, we are again going to plot it from the center. So if this was my electric field, this is my y-axis carrying the electric field, and this is my x-axis which is carrying the separation, that is the distance r. So if we move from center, that means if we move from r equals to 0 to any point, okay, to any point, that means r still being less than r. That means if this is the point which is r, this is the point which is saying ki r equals to r, so from center, that is 0 to r equal to r, we know ki electric field inside will be equal to what? It will be equal to rho r by 3 epsilon naught. Electric field on the surface will be equal to what? It will simply equal to k q by r square, where k was nothing but 1 by 4 pi epsilon naught, and again outside point, that means E out will simply be equal to what? K q by small r square. Here r will be equal to r, and here r will be greater than r. So essentially, if we are just plotting the variation, we can simply say ki in this point, that means between 0 to r equal to r, the value of electric field inside is directly proportional to r, because charge density is going to be constant, 3 is a number, and epsilon naught is also constant. That means electric field will be linearly increasing. And what is the linear graph? Yeah, linear slope. It will simply be increasing like this. Okay, and it will be stopping at this point. At this point, the value of electric field will be equal to what? K q by r square, which is also proven by this. If you are thinking ki sir, how will we get this value from this value, so you don't have to do anything, just write the value of charge density. Charge density will be equal to what? Q by V, and since the value of r at this point will be equal to what? Rho will be equal to what? Charge density by volume, which will be 4 by 3 pi r cube, right, multiplied by charge density by volume multiplied by r divided by 3 epsilon naught. That means 3 and 3 will be cancelled out. 3 and 3 will be cancelled out, and since r will be equal to r, we can just replace it by this. Then r will be cancelling out r cube, which will be r square, and the value will simply be equal to what? Q by 4 pi epsilon naught r square, which is nothing but this value only, but just we have put this in terms of k, and we have put this in terms of 1 by 4 pi epsilon. Okay. What will be the variation of electric field outside? That means from R to, let's say, infinity. What will happen? Electric field outside will be directly, yeah, inversely proportional to R square. That means it will having the graph of, something like this. Okay. So to summarize this all, I am just going to point it out. Key this part, that is on this on the surface and outside, is same. If you don't remember it, I'm just plotting the graph for the graph for all three, yeah, for 1, 2 and 3. The graph was what? Graph was something like this. Was the electric field, this was the radius. Electric field inside, that means from 0 to r equals to r, was not having any value. That you can also represent it by a different color. You can say the value of electric field inside was 0. Only after it reaches r equals to r, it jumps to electric field having a value of kq by r square, and after that it's jumping, yeah, it's decreasing by a factor of 1 by r square. Okay, so this thing, that means 1 by r square के inversely proportional होना, is same for the last case, that is non-conducting solid sphere, and all the three cases. If you don't remember, I am just going to point out what three cases were. 1 and 2 were representing conducting sphere, one was representing solid or hollow. You can just see whichever you want to say. So it was solid, it was hollow, okay, conducting sphere, and this was what? This was non-conducting hollow. So all three will be having this variation. Only this one will be having this variation, and even in that, till even in that, after the r equal to r value, that means when you put the value of electric field from the, when you look from of the value of electric field from the surface towards infinity, it will be same. Only the value of electric field inside will be directly proportional to r. That means it will linearly increase, reach the value of kq by r square, and again decrease in this manner as all the three cases were decreasing. So I hope you have understood the basic funda on how to solve all this. See, you can memorize everything. Okay, I am not going to say you should not do, but everything, once you have understood, once you can clearly see, it becomes very very easy, and that understanding will only come when you understand the basic principles. And for that also, if you are not getting the very idea, sir, what is Gauss law, how to approach problems with Gauss law, because I am just starting with the application of Gauss law. This is one of the applications of Gauss. So if you still don't understand what is Gauss law and how to apply it, we are going to make another video in which we are going to explain what is Gauss law and how to handle problems of Gauss law, and also some questions are asked based on electric flux. Okay, so we are also going to look upon the basic questions on electric flux. We are going to put our work, our basic understanding to test through those questions, those principles. So I hope you understood this. I hope you have taken a good look at it, and bye.